Good morning. Today we are going to our next part of the graph theory, that is tree. So today we'll discuss tree. So in this chapter we are going to discuss the fundamental ideas and properties of tree, which are very much important in computer science and electronics environment. The tree is one of the most powerful of the advanced data structures, and it often pops up in even more advanced subjects such as artificial intelligence, compiler design, and circuit theory. The difference between a tree in nature and a tree in computer science is that a tree data structure has its root at the top and its leaf on the bottom. There are two fundamental definitions of tree in use, a set theoretic one and a graph theoretic one. They are not equivalent. The graph theoretic definition calls tree graphs without cycles or graphs with unique paths between vertices. In set theory, a tree is just a set with a partial order such that there is always a least element. One can conceive a tree in this definition which does not fit the graph theoretical definition. Definition: a tree is a connected undirected graph without any circuits. A tree is a non-empty set, one element of which is designated the root of the tree, while the remaining elements are partitioned into non-empty sets, each of which is a subtree of the root. Following are the common uses of tree: manipulate hierarchy data, make information easy to search, manipulate sorted lists of data as a workflow for composition, digital image or visual effects, router algorithm. Few examples of tree. So one vertex, this is the two vertex graph without circuit. This is a tree with three vertices. This is a tree with four vertices. This is a tree with five vertices. Like this way. These are the examples of tree. Next definition: root. The topmost node is a true tree. Node that has a child, that is parent. Sibling: nodes with the same parent. Leaves: nodes with no children. Internal nodes: nodes with at least one child. Degree: number of subtrees of a node. Edge: connection between one node to another. Leaf of a node is defined by 1 plus the number of connections between the node and the root. Height: the height of a node is the length of the longest downward path between the node of a leaf. Forest: a forest is a set of n greater equals to 0 disjoint trees. Note: the edges of the tree are called branches. A null tree is a tree having no vertex. A tree with only one vertex is called a trivial tree. A collection of some trees are called forest. A collection of some trees are called forest. Eccentricity and center of tree. Let V be a vertex of graph G. The eccentricity of a vertex V, EV, is the distance from V to the vertex furthest from V in G. Mathematically, EV equals to maximum of Vi belongs to G, D distance D of V comma Vj. In the figure, distance between A and C 1, distance between A and B 2, A and D, distance between A and D 2, distance between A and D 3, distance between A and F 3. So E and F are the furthest from A. So eccentricity of A is 3. Eccentricity of B is also 3. Eccentricity of C is 2. Eccentricity of D is 2. Eccentricity of E is 3. Eccentricity of F is also 3. Now the vertex with least eccentricity in a graph G is called the center of the graph G. In the above figure, the vertices C and D are the two centers of the graph G. Next, minimally connected graph. A connected graph is said to be minimally connected if the graph becomes disconnected when one edge is moved from the graph. A minimally connected graph cannot have a circuit. So, minimally connected graph is a tree. This is the example of a minimally connected graph. Internal vertices of a tree. The vertex of a tree is called internal vertex, which is not pending vertex. In the above diagram, C and D are internal vertices. Binary tree, a tree in which there is exactly one vertex of degree 2 and each of the remaining vertex are of degree 1 or 3 is called a binary tree. The vertex of degree 2 is distinct from all other vertices and is called root. It follows that every binary tree is a rooted tree. This is the example of binary tree. This vertex has degree 2, this vertex has degree 1, this vertex has degree 1, this vertex has degree 1, this vertex has degree 3, degree 3, this is 3 degree vertex, 3 degree vertex, 1 degree, 1 degree, 1 degree, 1 degree, degree 3, degree 3, degree 3, 1 degree, 3, 1, 3, 1, 1. So this is the example of binary tree. Complete binary tree. A binary tree is said to be a complete binary tree if each of its internal vertices has exactly two children. So this is the example of complete binary tree. It has two children. So internal vertices has exactly two children. All the internal vertices we can see here. Every binary tree having the following properties. The number of vertices in a binary tree is always odd. The number of vertices of degree 1 in a binary tree is m. Then the number of vertices of degree 3 is n minus m minus 1, where n is the number of total vertices in T. The number of rooted binary trees with n vertices is 1 by n plus 1, 2n, cn. Now, there is a theorem proof that the number of pending vertices in a binary tree is n plus 1 by 2, where n is the number of vertices in the tree. So, let y equals to number of pending vertices in a binary tree. That is y equals to number of vertices of degree 1. T has exactly one vertex of degree 2 and each of the other vertices is of degree 3. So the sum of the degrees of all vertices of T equals to y into 1 because y number of pending vertices are there, y into 1. So, and in binary tree there is only one vertex of degree 2, so 1 into 2. And the rest vertices n minus m minus 1 is the vertices of degree 3. So that is why after that by Hansen theorem we know that sum of the degrees of all vertices equals to 2 into number of edges. So this is the sum of the degrees of all vertices and 2 into number of edges. If a tree has n number of vertices, the number of edges will be n minus 1. So this is 2 into n minus 1. So y equals to n plus 1 by 2. So if our binary tree has n number of vertices, then the number of n vertices will be n plus 1 by 2. And the number of internal vertices in a binary tree is 1 less than the number of n vertices. So let the binary tree contains x plus 1, x plus y vertices, where x is the number of n vertices, y is the number of internal vertices. So n equals to x plus y. So that is the total number of vertices. We know that number of pending vertices in a binary tree is n plus 1 by 2. So x is n plus 1 by 2. X equals to, in place of n we can put x plus y. X equals to x plus y plus 1 by 2. X minus 1 equals to y. So the number of pending vertices minus 1 equals to internal vertices. A binary tree. A tree has two vertices of degree 2, one vertex of degree 3 and 3 vertices of degree 4. How many vertices of degree 1 does it have? So its solution. Let y be the required number. Now the total number of vertices equals to 6 plus y. Hence the number of edges equals to 6 plus y minus 1, that is equals to 5 plus y. The total degree of the vertices 2 into 2. plus 1 into 3, because there is 2 vertices of degree 2, 2 into 2, 1 vertex of degree 3, 1 into 3, and 3 vertices of degree 4, so 3 into 4, plus 1 into y, because y were so y will be the required number, equals to, that equals to 19 plus y. So the number of edges 19 plus y by 2 according to the handshaking theorem. So 5 plus y equals to 19 plus y by 2, y equals to 9. So here 9 vertices of degree 1 in this tree. That is the answer. So thank you. This is our first lecture on